Yeah, very good morning. Today's our topic is Hooke's law. So this Hooke's law is developed by Robert Hooke's based on his experimental observations. It is developed by developed by Robert Hooke's based on his assumption, experimental calculations. So for doing Hooke's law derivation, we should know some assumptions. The first assumption is a chemical composition chemical composition throughout is same for the material. So entire material, the material property, all the chemical composition should be same. And second one is there is no temperature change. There is no temperature change while conducting experiment. And third one is there is no stress concentration. So stress concentration means the first assumption is the material property throughout the chemical composition is same and there is no temperature during the while conducting the test. And third one is very important. Stress concentration means, so we are taking a prismatic bar. So we are taking prismatic bar. So this means, for example, I am taking two different material. This is a prismatic bar. So this is a regular shape. So throughout this area, throughout this length, the area is same. This is a uniform cross section. Uniform cross section of prismatic uniform cross section. So another material is like, for example, this is a irregular shape. So this is a irregular shape. So this is called a non-prismatic and non-uniform and a non-uniform surface bar. So if you are taking this type of experiment, the stress concentration is more on this type of uh, uh, pieces, test pieces. For example, so I'm taking this small portion, I'm drawing this. For example, this is like this. This test bar is like this. If you apply the stress on load on this member, the more stress is concentrated here, because since stress is equal to force per unit area, means when the area is more, stress concentration will be less, because stress is inversely proportional to the area. When the area is more, the stress will be less on that particular area. For example, if the less the stress concentration is more. For example, if you are taking this type of workpieces for conducting this experiment, so what happened, the more stress is concentrated in this notch area. This notch area is clear, this notch area. So what happened, the first material will fail on here. So even the entire strength is more on the other than the notch, but the material will fail first on this area, because of lesser area more the stress is concentrated. This means there is no stress concentration. The assumption is there is no stress concentration, means we have to choose a uniform cross section prismatic bar. So is it clear? So this is our assumption. So what Robert Hooke say that the stress is, so based on his experiment, the stress is directly proportional to the strain. So the Robert Hooke observed this as an experiment, the stress is directly proportional to the strain. So stress is sigma is directly proportional to the strain. So for removing the proportionality, we should use some constant. For example, if you are using normal load, this is a normal force. For if you are using tangential force, so in tangential force, our stress is tau and directly proportional to the strain is phi. So for removing the proportionality, we should use some constant that we called as a E, capital E. Then capital E is equal to stress by strain. from tangential forces, again for removing the proportionality, we should use some constant. That constant we called as a G and strain phi. So then G is equal to stress by shear strain. So here E and G as the, here E is the Young's modulus of the material. Young's modulus or modulus, elastic modulus or modulus of Young's modulus or modulus of elasticity of material. Here G is called modulus of rigidity. So the units of E and G is the Newton per meter square. Since stress has the units Newton per meter square and strain has no units, therefore even there is no unit, the stress has a units of Newton per meter square and Young's modulus there is no unit. That's why whatever the units have the stress, Young's modulus also same units as well as a modulus of rigidity also. Is it clear? So this is a Hooke's law. So what is the physical meaning of Hooke's law? So by conducting this Hooke's law, the Young's modulus is equal to stress by strain. So we can write as a, so this Hooke's law and entire this stress strain, this Hooke's law we can represent in a stress strain diagram. Stress strain diagram. So we can represent this Hooke's law in the stress strain diagram. So how we can represent this stress strain diagram in a the Hooke's law is we can represent in a stress strain diagram. So here our stress strain diagram is indicates stress is the function of strain, because we are observing here based on the Robert Hooke's experiment, the stress is directly proportional to strain, means the stress is the function of strain. So it's look like a y is equal to mx plus c. So according to this stress strain diagram, if you draw the stress strain diagram of any material, this is a stress strain diagram. In y-axis we represent stress, in x-axis we represent strain. So it is look like a straight line equation. So our stress strain diagram is like this. So this represent a Young's modulus C. How we can represent? For example, this is x, this is y. So this is equal to slope m. This is a slope, m is equal to slope. So this is a slope, m is a slope here. Is it clear? So likewise here the E is the slope. E is the slope. So it's a straight line equation. It's look like a straight line equation. So y-axis, so it's same as a sigma is equal to, so by doing this, Young's modulus E is equal to stress by strain, then Young's modulus, then stress is equal to Young's modulus into strain. We can write as a E into E. So this is nothing but to y, this is nothing but to x, this is nothing but to m. So it's look like y is equal to mx, so some constant c. So this is a, so then that's why the strain will represent in x-axis, the stress will represent in y-axis. This is a slope. So this is called slope of this material. So this is a stress strain diagram. This is a basic representation of stress strain diagram for any material. Is it clear? Now, so our actual stress strain diagram will be, so according to y is equal to mx plus c, so the strain will represent in x-axis and the stress will be can represent in a y-axis. So this is called our slope. So this is our slope Young's modulus E. So this point is called a proportionality limit. Proportionality limit. So the Hooke's law, therefore, Hooke's law is valid up to point A, that is called proportionality limit only. So because this is a straight line equation, this is a straight line, this is everything is straight line. So this Hooke's law is only valid up to this point A, that is called proportionality limit. So is it clear? So therefore Young's modulus E is equal to stress by strain, then stress is equal to Young's modulus into strain. So this is everything is called Hooke's law. So here E is called Young's modulus and G is called modulus of rigidity. So what is the exact physical meaning of Young's modulus? Physical meaning. So let us take, I'm taking two different materials. So this is material A. I'm taking this is a steel. I'm taking two different materials with the same geometrically properties. This is rubber. So assumption here, same geometrical material. So same geometrical material means length and area are same. So initially this is the length L. This is also same length. So the right side is the rubber and the left side is the iron. So this is also area A. This is also area A. So now I'm applying the same load. So I'm applying same load. I'm applying the same load. So I'm applying the load P. I'm applying the same load P. Is it clear? So what you can observe that if you're applying the same load, for example, if you're applying the 100 kgs of load for both steel and rubber, what you can observe? The steel is deforms less and rubber will deform more. Likewise. So this is a deformation of rubber and this will be the deformation of steel. So what is this called? Change in the length of steel. This is a change in the length of rubber. So even you apply the same load for different materials, same geometrical materials means same geometrical means both length and area should be same. So if you are applying the same load for different material, so the steel is the less deformed and the rubber will more deformed. So we can observe here delta rubber is greater than delta L steel. So this is our first note by conducting this experiment. So I'm taking this as a equation number 1. So we know since we know Hooke's law, what is Hooke's law? Stress is directly proportional to the strain. So then stress is equal to, for removing the proportionality, we use the Young's modulus E, and then E is equal to, so we know that stress is equal to load by area and strain is equal to change in length by original length. So we can substitute here stress is equal to P by A and Young's modulus E into delta L. E strain is equal to delta L by L. So we can note that delta L is equal to PL by AE. So from this equation, we can make this delta L is equal to PL by AE. So here, so from taking this, so delta L B is greater than delta LS. Is it clear? So making this delta L is equal to P of PL by A E Young's modulus of rubber Young's modulus of rubber and is greater than PL by A Young's modulus of steel. Since P is the same for both the material, I am applying the same load for the both the material, and A also same and length also same. So by cancelling P, P, L, L, A, A. So what we are getting, 1 by ER is greater than 1 by ES. So from trimming proportionality, we should use Young's modulus of steel is greater than Young's modulus of rubber. So this is our equation 2. Is it clear? So from the equation 1 and 2, what we can conclude? So I'm taking two different materials, steel and rubber, having a both geometrical properties like length and area. So I'm applying the same load. Is it clear? So the steel will deform less. You know that everything, you know that general, this is general concept. As a general concept, you know the steel is less deformed than rubber. So delta LB, so change in length in rubber is greater than steel. Is it clear? So I'm taking this is a derivation. So what we can conclude? So our conclusion is nothing but, so our conclusion is delta L of rubber is delta L of steel is less than delta L of rubber. Yes. So deformation of steel is less than the rubber, and Young's modulus of steel is greater than Young's modulus of rubber. So what we can observe here, more E is leads to delta L is less. So if E is higher, Young's modulus will be less. If he is lower, delta L is more. Means Young's modulus of steel is greater than rubber. So higher the Young's modulus of steel, lesser will be the deformation. Lesser will be the Young's modulus of rubber, higher will be the deformation. So what we can observe, if the E is high, delta L is less. If the E is less, delta L will be more. So this is we can conclude. So that meaning, so physical meaning. So from the diagram of stress strain diagram, so we can make this. This is a stress strain diagram. This is strain. This is a stress. This is the slope. So here E is the Young's modulus, is nothing but a slope. So higher E means higher slope. Am I right? Lower E means lower slope. Am I right? So we can observe here ES is a Young's modulus of steel is greater than Young's modulus of R. So Young's modulus E is nothing but a slope of this stress strain diagram. So higher the E means higher the slope. So by making this conclusion, so this is a Young's modulus, one Young's modulus. This is the another Young's modulus. So higher the slope, which one is the higher Young's modulus? Steel. Which one is the lower Young's modulus? So Young's modulus of steel is greater than Young's modulus of rubber. So higher the Young's modulus means higher the slope. So this is a Young's modulus of steel. This is a Young's modulus of rubber. So higher Young's modulus material is always near to y-axis. This is called sigma. So lesser Young's modulus material is always near to x-axis. Is it clear? So our physical meaning is, so by conclusions we can make that more Young's modulus more the Young's modulus of material, more the Young's modulus, material will deform less. If Young's modulus is less, that material will deform more. Is it clear? And second one, so Young's modulus represents stiffness of the material. So by observing these diagrams, Young's steel will deform less, means it has a more stiffness. This is a less stiffness. So lesser the stiffness means more will be the deformation. More the stiffness means lesser will be the deformation. That means higher the Young's modulus. So Young's modulus represents a stiffness of the material. And so another physical meaning is Young's modulus represents resistance offering on axially loaded member. So since here you can observe here the loading is axially. So for applying the axial loading, higher resistance is applied here, generated. Is it clear? So this is a physical meaning of Young's modulus. Okay, another important point I forgot here. Sometimes stress is directly proportional to the Young's modulus. How it is? So since stress is equal to P by area and strain is equal to change in length by original length. So what Hooke's law state that stress is directly proportional to the strain. So then stress is equal to Young's modulus into strain. Strain is equal to stress by Young's modulus. Strain. Young's modulus is equal to stress by strain. So we know that if you apply load, definitely there will be a deformation of a body. If a body deforms double, means this is an example. Initially this is a 10 centimeter body of length. So when you're applying the load, so this is constraint, applying the loads some 10 newtons, so the body will be deformed. So initially this is a 10 centimeter. Now the deformation, this delta L also same as L. This means 10 centimeter. This means double means how much initial length is there, that same amount of deformation is takes place, and delta L is same as L. So when the material is deforms double, so what happened? Then strain is equal to delta L by L. Delta L also 10, L is also 10. So what happened? Strain is 1. So in that case, Young's modulus is equal to stress by strain. So then Young's modulus is equal to stress by strain is 1. Therefore Young's modulus is equal to strain. So in some cases, the Young's modulus will be same as the stress. So that case should be the deformation is double when you apply the load. Is it clear? Okay. So next topic is elastic and plastic materials. So what is in by elastic material? What is in by plastic material? For example, I am taking a material. So I'm taking a material here. So applying, so I'm constrained here. So applying the load. So what happened? This material will deforms like this. So deforms like this. So initially this is a L of length. So after this is a final length LF. So there will be a deformation delta L. So when you are removing this load, so when P is equal to 0 means when you remove this load, if the material comes back as the same position, that is called elastic material. So when you are taking a material, when you apply the load, the material will deform. After removing the load, again it's come back to original material, original position. So same length L, that is called elastic material. Is it clear? That means next plastic material. So plastic material means I'm taking a material, I'm applying the load, definitely there will be deformation. This is the L. So after applying the load, what happened? This will be deformation is takes place. So this is a deformation delta L. This is the original length L after applying the load. Is it clear? So if you remove the load, the delta L does not equal to 0. This means it does not come back to original position. Since the deformation stops even if you are the deformation in the same position after removing the load. That material is called plastic material. Is it clear? Now the next topic is types of stress, strain diagrams. Types of stress strain diagrams. The first one is linear elastic material, and second one is a rigid material, and third one is a ideal plastic material, fourth one is a elastic material, and the fifth one is a rigid plastic material. Is it clear? The first one is a linear elastic material. So as seen in our stress strain, like common stress strain diagram, this is a linear elastic material. So the material will linearly changing its dimension. So this is a linear elastic material stress strain diagram. For rigid material, so rigidity means there is no deformation. Means for rigidity, E is equal to 0. So therefore E is equal to 0 means E is equal to 0 means there is no deformation in x-axis. Is it clear? So the material is looks like only when you are applying the load, the stress will be only there. This is a only, there is no E. This is a rigid material. And next one is a ideal plastic material. So ideal plastic material means the deformation is continuous. Plastic material means the deformation is a continuous. This is a strain, this is a stress. So for ideal plastic material, sigma is 0. So looks like, so there is a deformation, continuous deformation is there means there is a strain. There is no sigma. Next, elastic material. So elastoplastic material. Actually, this is elastic plastic material. So the material stress strain diagram follows two stages. The first one, up to proportional some point, this is a linear elastic. Then it is follows like this. This is a elastoplastic material, and last one is a rigid plastic material. So rigid plastic strain stress. So rigid means there is no E is a zero. Rigid means E is zero. So therefore, our stress strain diagram is looks like that. So it's coincident on this, and ideal plastic means this is. So this is for rigid, then it's going plastic nature. So today I will stop this class for this section.